Let us discuss a question from thermodynamics. Okay, so basically this is again a question on Rankine cycle. A steam smaller power plant produces 25 kgs of, so this is mass flow rate 25 kgs per second at boiler condition. So we assume Rankine cycle and we draw the dome in a TS diagram, S and a TS diagram. So same thing, it goes like this. The higher pressure, these are the constant pressure lines inside the dome, they are constant. So this is at 3 MPa and at 3 MPa 600 degrees Celsius. So we assume it's like this. This is 3 and then it comes, and this is 4, which is your condensate pressure. Condensate exits at 45. The state properties of these are at 45 degrees Celsius. This is 1, and then you have some pump work that is done before entering the boiler at 2. So now what we do is the net power. So first we'll start with 1 to 2. Process 1 to 2 is a reversible adiabatic process, and the pump work in a reversible adiabatic process. Pump work in an open system is given by integral minus integral VdP 1 to 2. And so this is the pump work, that's why it's negative, okay, minus. And so what we do is we just write down plus here because it's work done on the system, that's, and we'll subtract this pump, okay, work. So integral V is specific, so V specific volume doesn't change much, so we assume that there is a specific volume at the start which is at 1, and that is nothing but Vf. So that is 0.00101, and P2, the pressure is, we will write in terms of kPa, so it's 3000 minus P1 is basically pressure at 1 is given at 45, the Psat is 9.59, so that is 9.59, yeah. So this V integral VdP, so this value comes about 3.02, it's kilojoules, okay, per kg. We'll first do everything in per kg and then we'll just multiply with the mass to get the power developed, okay. So this is kilojoules per kg. You got the pump work. Now we are interested in 3 to 4 because net power, so we will just concentrate in process 3 to 4 so that we get the turbine work, and therefore the turbine minus the pump is the net power delivered. Now H3 is something which is already given. The turbine work is basically in an open system, it's difference of enthalpy H3 minus H4. H3 is something which is already given at 3 MPa. Okay, the value is at 3 MPa, the value is 3682. Okay, it's a superheated value, 3682, and HS3 is basically, it's a superheated, so 7.5082, 7.5084. okay, so this is 0.34 kilojoules per kg, and this is kilojoules per kg Kelvin, okay. So this is S3. Now remember that again we have to decide that whether 4, how much is the dryness fraction at 4, because then only we can get H4, because we don't know H4. So first what we do is we use the property of the process which is reversible adiabatic, that S3 is equal to S4, and S4 can be written as S4 at 9.59 kPa plus dryness fraction. This is how you write the properties of wet steam, S4 Fg, right, and that is also at 9.59 kPa. So let's put the values because entropy is same, it's a reversible adiabatic expansion. So 7.5084 is superheated entropy, and the value is so this is 0.6386 and 7.52. So 0.6383 plus dryness fraction into 7.5. Let's go again and look at the values at the top. 6386 7.5261. Okay, so when I calculate dryness fraction from this, dryness fraction comes out to be 0.9128. So I got dryness fraction. Now H4 is basically HF. Okay, HF at 9.59 plus the dryness fraction into HFG at 9.59. So these values are given, and these values are basically these: 188.42, 2394. So 188.42 plus 0.9128, and this value is 2394.77. So this value actually comes out about 2374.4. This is H4. So now we use this expression to get the work done of turbine. H3 minus H4 is 3682.34 minus 2374.4. So this value comes about 1307.94, and so the net work is WT minus pump work, because turbine some portion of the turbine work goes to the pump, so that we need to subtract it to get the net power delivered, is 1370.94 minus the pump work, which is basically 3.02. Okay, pump work is very, very small. So this comes about, and so this is, and now in order to get, so this is 3.02, so this is about 1304.94. okay, and we need to get, this is in kilojoules per kg, so but we know the mass flow rate, so the net power developed is mass flow rate into the net work done, and that is given as 25, okay, into 1304.94. so this roughly comes about 32,620. when I multiply, roughly it comes about that 3262 kilowatt, because it's kilojoules per second, and therefore, but we want in megawatts, so it's 32.62 megawatts. So 32.62 megawatts is the answer. 32.62. 2.62. So this is again a Rankine cycle based problem. 32.62 megawatts. Thank you.